Any questions before we start? All right.
We're 4 strong today.
I don't like paper. That's their kid testing.
So, let's kind of go through what we were doing last time. So, here's the theorem. I won't repeat it entirely. Left or right, or two-sided. Properly contained in R. And I think so this is what we got most of the way through last time. So let's kind of go through a little bit of what it was about again. And the key here is we use this Zorn's limit, this thing is called the axiom of choice. So what we do the first thing I do is I gather up a partially ordered set, or as some people call it, a pose set, of the collection of ideals, or left ideals. I'll drop the word left. Assume you can put that modifier there. Left, like that contain I and are properly contained in R. Now, this is truly a partially ordered set, or I would expect that to be true in general, because if here's I, and here's R, there might be some ideals that contain it that are comparable. So notice that J2 contains J1, but there might be others that contain it. I3 that, notice that J3 does not, well, notice J3 does not compare to J2, even though it does compare to J1. And here, let me throw a little something on it. I didn't compare to either. But every time you can compare apples, then it satisfies 3 things. If J1 is contained in J2 and J2 is contained in J1, then they're equal. You have transitivity. J1 is contained in J2, J2 is contained in J3, and J1 is contained in J3. Right, and J1 is contained in J1. So you got all those things. Now, what we have to do to apply Zorn's lemma is we need to show that any chain in this set, and that just means a totally ordered subset. So I'm pulling out all apples or all oranges, no mix. So I'll go from partially to totally ordered by looking at the subset. Every chain must have an upper bound that's still in gamma. So here's our chain, and the fact that it's a chain means that J alpha is contained, well, let me say for all alpha beta, and this index set, one of these 2 things must be true. Pull out 2 of these ideas at random, one of them contains them. Okay. Now, we need to find an upper bound for this change C. So let us do what I think is probably, I mean, it's bulldozery, right? I mean, you're just kind of doing, you know, throwing the kitchen sink at it, but let's hope this works. Just take the union of this chain, and I'm gonna call this U. Now, I claim that that is my upper bound for my chain, and that it's in gamma. Right. Now, first, I should get a little bit of the shakes here, a little bit nervous I am, because in general, I do not expect the union of ideals to be an ideal. In fact, this is usually not true. I think if you have two, even if you have subgroups of groups, let's just say you have a billion group, you have two subgroups, then the union of those two, or H and K, is a subgroup if and only if one of them contains the other. That's exactly what we have here. This chain is going to save our butts. So the first thing I do is I need to clean this is an ideal. So number one, X, Y be in this thing. Well, since X, Y are in U, which is a union, that means that X is in one of these J alphas and Y is in some J beta. X, J beta, Y, and J gamma. And here's the part where I use that this is a chain. Because one of these two animals has to contain the other. Therefore, X and Y are, let's see which one's the small one. They're both in J gamma. Y is in J gamma straight up, and X is in J gamma because it's in J beta, which is contained in J. Therefore, so I've shown the difference of two elements in this ideal, or in U is still in U. So U is in fact a subgroup. So there's a subgroup criteria. And two, note Rx is in J beta, which is contained in U. Therefore, U is a what that? Ideal. So it's a subgroup and it vacuums up from the left. Okay, so far? Now I'm not quite done because let me observe what else you have. Also, alpha in the index set, alpha is contained in U. And so that means that ostensibly U is an upper bound for this chain because it is greater than or equal to, that is, it contains everything in the chain. Now I'm not completely done yet because I really need to show that U is in gamma. And for U to be in gamma, it's got to satisfy a couple of things. Number one, U has to be a left ideal. Ding, ding, ding. We've already shown that. Two, we need to show that this left ideal in fact contains I. That's one of the criteria for membership. And the last thing we have to do, let's see, we've shown it's a left ideal, we know it contains I. We need to show it's proper. That is to say, we need to show it can't be R. And number three, note, Yep. And one here, because we're assuming here that R was a ring with identity. Therefore, one is in U, which is the union. Therefore, one is in J alpha, some alpha. And this is a contradiction. J alpha is supposed to be strictly R. So, where are we? We know that U is an upper bound. We know that U is in gamma. And C. And gamma. So, by Zorn, gamma contains what does it mean to be a maximal element? So there exists maximal idea of R. And that's how you use Zorn's law. We're going to use this again a couple of times on some other results. Okay. Any questions? Let me give you a couple of examples. For many of your garden variety range that you would start off with or see in like a beginning algebra class or number theory class, this theorem may seem silly because it's like, oh my goodness, you can pick out maximal ideals. I don't need the axiom choice to produce those. Right, there it is. Yeah. If you have a field, if that is a field, and you look at polynomials and three variables over that, and the ideal generated by the three variables is a maximal ideal. The easiest way to see this, another way to characterize this is all polynomials. And when you plug in 0 for x, y, or z, you get 0. So we constant term is 0 essentially. If you want to prove yourself it's a maximal ideal, just take this ring on this ideal, and you will get the field that nice and more. But there is actually something here. Number 3, and we're going to talk about this more formally in a moment. This is a homework problem. Think of this as infinite vectors, all with entries 0 and 1. I've got complete freedom. This example really shows, and I won't ruin your fun because you should work through the homework and see this. I can list some maximal ideals here. For example, the ideal that consists of all vectors that have 0 in the first coordinate is a maximal ideal. Or the ideal that consists of all zeros in the second coordinate is a maximal ideal, et cetera, et cetera. However, if you look at the ideal, if you look at the, it's easy to show that the direct sum is also an ideal. Remember, the direct sum means that everything has to end in an infinite string of zeros, in the countable case. Then what that means is this ideal actually is contained in a maximal ideal by Zorn's lemma, but it's not contained in any of those ones that I just listed off. And in fact, good luck ever writing this down. It exists, but you have to make infinitely many choices. And I'll tell you something else that's interesting. I stumbled actually across this. I've wondered about this for a while, but there's actually a paper from 1976 that shows, yes, for the integers, I can list the maximal ideals. How many of you have heard the phrase principal ideal domain, PID, right? It's like, it's an analog of C. It's a ring in which it's an integral domain, in fact, where every non-zero ideal is principal. You cannot prove that a principal ideal domain has a maximal ideal in general without the axiom of choice. It is required. That's actually been shown to be a necessary condition. So we really did kind of do something. Any questions so far? Okay. And I am actually going to talk about direct product, but I want to give a couple other theorems kind of interest, mostly without proof. These are slight generalizations of some stuff that we did here. Here's the first generalization. Let R be a commutative ring. That R squared equals R. Notice that this condition is always satisfied if R has an identity, but it can be satisfied if R doesn't have an identity. So this is a slight generalization of the statement has an identity. This is just a little bit more general. Then any maximal ideal of R. We already know that maximal implies prime for rings of one, but this is a slight generalization. In this situation, maximal still implies prime. Theorem. And here's another slight tweaking generalization. The ring of one. And all a proper ideal. Number one, if M is maximal and R is commutative, then oh my God. And B, or two, if R mod M is a division ring, then M. So the upshot is this: we already knew this actually. If M is maximal and R is a ring of one, so if M is maximal and R is commutative, then you know that R mod M is a field. We knew that. But here's something that gives you a bit of a converse. If the quotient ring is a division ring, then M is maximal in this situation. Let me make another remark. And this will be useful actually we get on to 8520 actually. So if R is 1, then M is maximal. If and only if R mod M. Again, this is a result we had earlier. We looked at quotienting out by ideals. And R itself is a field. R has no non-zero proper ideals. Right, non-zero proper ideals. If and only if zero is maximal ideal. If and only if every ring homomorphism F on S let me say every non-zero. Right, because the ring homomorphism for S must have some kernel, and that kernel is an ideal. So if zero is maximal ideal, that means the kernel is zero. Some people, depending on what the context you're working in, sometimes demand that a ring homomorphism takes 1 to 1, and so I could have left in that context. I could have left non-zero off that. Okay. Okay, so here is, I brought this up by example 4. Let me formally write something down for you. And it's good that I'm writing this down here because actually we're going to proceed from here. This is kind of a segue into the famous Chinese Remainder Theorem, right? How many of you have seen Chinese Remainder Theorem? At some point you saw it in you're going to see that in an algebra class at the beginning, or maybe a number theorem. And we'll see it probably a little bit more generally here than the old days, perhaps. Well, Ri the family of rings. And our product underlined. So at the beginning of this construction, what I'm saying is forget about the fact that these are rings, forget it. These are all just abelian groups under addition, right? And let's just look at the direct product, right? And of course, again, this is just a set of all next RI, where each full of RI is in capital RI, and I've got complete freedom on the input here. A, this direct product of abelian groups element down here. Is a ring under pointwise multiplication. So what I mean by that, the Ri times Ri prime is Ri prime. I love math, right? You just do the easy thing, right? So under pointwise multiplication, this is a ring. And B, we can only the identity of this ring, if and only if each RI has identity. Let me point out that the identity of the direct product of RI is the net of I RI. Right, that is to say, to make them multiples of identity, I just put the one in every coordinate, if you will. C, number C, for all K in the index set, K from the direct product given by K of the net RI, which reads the K coordinate, is a ring epimorphism. And D, for all K in the index set, the inclusion iota K that goes from RK product given by iota K you say better. Yeah. So my input is something here. My output must be one of these nets where I need to find this. And then, oh, I need completion. Is a monomorphism. Let me point out that you can do the same thing. Do the same thing for a direct sum as well. What do you suppose might be a sort of a big sort of change point between direct product and direct sum? there's a major difference. Well, you get more of a hint. There's a major difference when the index set is infinite. I guess it's here in B. That's probably most of all. Let me point out that if we have the direct sum and the index set is infinite, you can't have an identity. Everybody agree with that? You got a real problem with having the identity because you're really forced, the identity condition really forces you to put a 1 in every coordinate, right? If you have an infinite index set, this is impossible. And of course, if you have a finite index set, then the direct sum and the direct product are the same. Now, what's the relationship between the direct sum and the direct product if you have an infinite? They're the same if you have a finite index set. If you have an infinite index set, what's the relationship? Well, it depends on what you want your terminology to be. The direct sum is in fact a subring of the direct product, but it can't have an identity. So if you want to demand that subrings have to have identity, some people do, subring, but for sure the direct sum is an ideal. So see if you can check that. If I look at the subset of this, the direct sum, it's an ideal. That'll come up in your homework actually. Okay, any questions so far? So there. Let Ri be a family of rings, S a ring. S a ring. And a family of homomorphisms. And again, we can certainly allow the zero homomorphism, right? But demonstrates the thing of identity. And there is a unique let's say capital P and S into the direct. That has property so I do so love writing diagrams of this. So what we have is we have S so what I have here is I have homomorphisms from S into lower I, and actually K. And what else do I have? I have projection maps. So by hypothesis, I have all these homomorphisms go from S to Ri. I also have my projections from the direct product. And so there should be a unique homomorphism, P, that goes from S to Ri, such that when I do P and then I do pi k, it's the same thing as this. So I'll tell you the punchline first, so you can verify this. We've already done this actually for a billion groups. So if I just forgot about everything except these being a billion groups, then I'm done, right? So the only thing I really need to do is inspect to make sure that the speed that is defined for a billion groups is extended to a nice ring homomorphism. And of course, here's the way it has to work. You will find this familiar. This is what we did before. B of S has to be some kind of net. And there you go. And just check that thing. Just check that thing works out multiple. You're good. Okay. Any questions?
So this is the universal mapping theorem for ring, right?
Get to some fun stuff, factorization here. Five, 3, 6. Suppose that I have ideals in R. Suppose I have a ring and I've got a collection of ideals, finitely many of them, such that number A that is, when I add the ideals up, when I look at this sum of ideals, I get all of R. And 2, if I take any one of these ideals and I intersect it then R is isomorphic to ring A1, A2 as a direct product. This is a very useful thing, and this probably looks familiar because we have a similar kind of thing with groups. We try to find out when is a group a direct product of two of its subgroups, or more generally n of its subgroups. Well, when you put all the groups together and see what they generate, you get all of the group, and there you go. And when you intersect any one of the groups with what's generated by what's left over, you get 0. Then R was the direct product of the group. By the way, we already know that this theorem is true just on the group level. We just don't know it's true on the ring level. So before we do this, so for example, I think it's interesting on the ring level, I think, is let me Let me underscore a couple of ideals here that have this property. That's the ideal generated by 2-bar. And let me put my key needs for another color. Anyway, so I'll put boxes around this other one. Notice that 0 bar, 2-bar, 4-bar is an ideal. It's certainly a subgroup, and it vacuum planars because when you multiply anything by that even cosine, it's even. And 0 and 3 is a subgroup. It's also a vacuum planar. Notice that the intersection of these two is 0, right? Because the only one that's circled and boxed is 0. And when you put them together, you get all of R. Notice that both of these are ideals. The ones in the box and the ones in the circle are both ideals. Neither one of them contain the identity, but when you put them together, they do contain the identity. Because notice that so when you put these two ideals together, boxes and circles, then you have to have 3-bar plus 4-bar, which is 1 bar. And any ideal that contains 1 bar, so you're generating an ideal, any ideal that contains 1 bar is the whole thing. So you're good to go there. Okay, so let's so I'll go through, I probably really don't need all this detail, but it's not, certainly not hurting. Consider map phi that's given by actually, yeah, so my input is actually I guess I sort of spoiled the surprise here. What's the most intelligent way I can think of to take this in tuple and get it to bark out something in R? Well, I do know that every one of these AIs are in R, so each AI is in R, so I'm stat them up. And input in tuple, output something in R. Well, only one person. We've actually already seen this, right, back in the group theory days. And the reason this is because anything in R can be expressed as a sum like this. And so take your favorite element of R, however you can write it as a sum, that tells you what the input is and it's on, right? Easy enough for it to be onto. The trickier part is why is it 1-to-1? Let's look at the kernel. I know it's proof homomorphism. Those. close that is 0. So what does this mean? Let's just kind of massage this equation here. AI is negative A1, let's say 2, let's say I'm not 1, plus 1 is n, which is n. And because look at AI, it can be expressed this way, so it's in this thing. And of course, by definition, it's in AI. So this thing right here, AI is in this intersect AI, which is 0 by assumption. Therefore, each AI is 0. So kernel B. So B is 1. So the only thing really left remains, let me make sure that I got all my details and worked out here, is I need to show that this is a homomorphism with respect to multiplication. That's, I mean, basically everything that I've done so far is just to prove for abelian groups. And that allowed me to get group homomorphism 1-to-1 and onto. So let's check this. I hope my notation is suggestive enough. Each AI and each BI is both in capital AI. This is equal to B, A1, B1, A2, B2, AN. Now, at this point, this should probably scare you a little bit because of cross terms, right? So here's what I mean. This should equal now. What's scary to me is this. If this is all correct, then my next step has to be correct. And listen, after my lecture, then you guys got to sit here and wait for me to erase the board. They'll in your algebra class coming in next time. And when they see that crap, I'm in big trouble, right? I mean, this doesn't work in general, right? Because you've got all kinds of these cross terms, right? You've got like A1, B2, and so forth, so on. But it's not an issue. Anybody coming by. Yeah. A-I-G-J. Yeah. is actually contained in AI. These are ideals, right? Vacuum cleaner, everything in this product is an AI. Vacuum cleaner, everything in this product is an OJ, so it's the intersection. And this, zero, by this assumption. Because not only is AI intersect AJ, actually AI intersect the whole sum of everything left over at zero. So this is going to be zero as well. And so this is bona fide. Everybody okay with that? Everybody see how this works? Okay, any questions? How about out there? Any questions out there? All right, well, if there aren't any questions, you all have a good one, and we will see you next time.